All right, welcome to another episode of the Concrete Logic Podcast. And today I have Bill Kulish from Steel Like with me. And when we have Bill on, we talk about ultra high performance concrete or composite, however Bill wants to explain it today. So we're going to talk about that today. And as always, I just want to remind you how you can support the show. You can do three or four, or all of them, or one of them, or any of them. But first thing you could do is, if you enjoy the podcast, please share it, get the word out there. So share it on any of the platforms you can listen to the podcast on. I don't really like Apple, so I do these album arts. I don't know if people notice them or not. But the one that I released this week, the album art didn't come across on Apple, and I checked the other ones, the other platforms, and it came across. So I don't know, Apple, you're screwing up. So that's the first way. Share. Second way is if you go to the concretelogicpodcast.com homepage. There is a couple ways to get a hold of me. There's a contact linked at the top. You click on that, and then a window opens up, and it's like leaving me an email. So you go in there and type in there. And then on the bottom right-hand corner, there's a microphone little symbol thing. You click on that, and it lets you record on your computer a voicemail. And what I like to get from you is topic or guest suggestions. So if there's somebody you want me to talk to on the podcast, or there's a topic that you want us to talk about on the podcast, please reach out and let me know. Those first two things are really a big deal. So it helps the podcast immensely. And then the third way is there's a donation button. It's in the top right-hand corner of www.concretelogicpodcast.com. You can click on that, and you can give any dollar amount. I've had folks reach out. They give $10. They give, $20. I've had someone give me $600, which was great. Any amount is appreciated, and that just helps pay for the equipment, this interface that we use. We use Riverside. It pays for that. It pays for there's some other things that we do for as far as editing and other things. So it helps pay for all those things. But the deal is I put these podcasts out there for free, and because I don't want to charge folks to educate themselves about concrete. I think it's very important. So that's why I put it out there for free. And if you think there's some value out of that, you have an option there to do that. But again, appreciate all the support I've had so far, coming up on 3 years of the podcast, and 100. We're recording episode 112 right now with Bill. So it's been a good journey so far. Bill, let's talk about ultra high performance composite or concrete. And today, on past episodes, we talked about the bridge application for UHPC. So I think where we should start off is if you could explain again what UHPC is, how it's different from traditional concrete. If we can start there, and then we can talk about those new applications that you wanted to discuss today.
Good morning, Seth. Thanks for having me on. I'm always a pleasure to be on this side of the camera and then to watch you on your many other podcasts. I learn every time. It's great also to see challenging standards and Dr. John expressing his opinion, qualified opinion. So thank you for that. UHPC.
Yeah, I don't want to interrupt you, but I think you just hit on something important here, and that's kind of the purpose of this podcast is ACI. They put out the standards and now codes. They like the word code now. They put those out for us, for the industry. They have their own podcast. You should go listen to their podcast. I forgot the lady that does their podcast, but you can listen to that. What I promise you is they won't go on there and probably critique their own standards or codes on their podcast. Um, that would seem like that would be shooting themselves in the foot, because they sell you. We all have to buy their standards and codes to read them. And if they say, hey, they're critiquing them, I don't know. Maybe they will. Maybe I'm wrong, but that's kind of the purpose here, folks, is for people to come on here and let's talk about things that I hear when I talk to people offline, complain about things, or say, hey, we should try doing these things, or these are my challenges and I wish this group or that group would help out with these things. That's what the podcast is for. So when you go to the website and you're sending me topic and guest suggestions, don't hold back. Just tell me what you want to talk about and what you want to hear. Because I think what Bill just said is, that it's important for us to talk about these things, and it's not like we dislike or hate or are negative about those things. I don't need that on the podcast, but I think we need healthy discussions and debates about things that are shaping our industry. And if we don't talk about them and we don't discuss them and debate about them, there's people that don't know squat about concrete that are going to dictate the concrete we get. Yep. And then I mean, we're already dealing with that kind of now. So yeah, we all need a voice, what we see out there, and what not just the bad things too. We need to talk about the successful things. So sorry, Bill, I'm off my soapbox now. You can go.
No, I digress off of your digression. So quick example is 1L, right? It's just a 1-to-1. Throw it in there. Nobody. Let's reduce carbon footprint. Meanwhile, we may be producing material that increases the carbon footprint because it doesn't last as long, or it takes more money because it doesn't mix and place the way it should. There's these real world challenges in between what academia sees and what the guys on the bridge are actually doing. And the more conversations we have about it, the more everybody wins, right? It's not us against them, as you said. It's all of us dealing with the reality. And if there's a code or an ASTM protocol for testing, it has to be achievable. What good is a regulation if it regulates innovation out of the picture, or if it creates problems? And by talking about it in open forums like this and your podcast, it's refreshing. I mean, otherwise I'd just bang my head against the wall, or it is what it is. So back to UHPC.
Yes, sir.
Not as exciting as what you just said, but we'll make it exciting because it can be. Ultra high performance concrete, ultra high performance composite. It's not a mortar. It's not slurry. It's not grout. It's not traditional concrete. The biggest ags are like the diameter of a human hair. So we have like thousands of human hair sized particles, sand and such, for every 3/4 inch stone you would normally have. We decrease the water below 18% water, cement ratio, but because there's multiple binders, we just say water binder ratio, right? Yes, we're using type 1L cement. It took a year to figure it out, but it getting better results now after a lot of modification and R&D. It's a discontinuous pore structure. So we don't have a bunch of air connecting with other amounts of air. On average, we have less than 2%. I'll speak to steel. I have less than 2% air content. I don't want air. If I don't need to add air for freeze thaw, because it's so dense and there's discontinuous pore structure. There's no air connecting the tunnels. Because we don't have a lot of water, there's no evaporating bleed water that creates channels. What we end up with is a material that's waterproof, not water resistant. We end up with a material that's salt proof, not salt resistant. And if water can't get in, it can't freeze. So it's just, it's got tensile properties, mostly due to the type of steel fibers that you would use. So it has strain hardening characteristics. It has similarities to steel. One could say it's like steel, wink, wink. So what we have is an extremely high compressive, not brittle, something that withstands freeze thaw, real world stuff. You can put an inch of it over a bridge and you're good for a couple hundred years. So it's a different material. It's much more expensive. The elephant's not in the room because we got a big circus tent and we're talking about reality. So it's expensive. But, in 50 years, it reverses the carbon footprint. If you factor in inflation and everything else and traffic detours and all the stuff that would be needed to repair something, if you don't have to repair it, that money is in your pocket. So it's more upfront, less over the life cycle cost because the life cycle goes far greater than most materials. That would be a high summary of what UHPC is as compared to normal concrete.
Yeah. Well, I think when we say expensive, I think you have to kind of peel that onion a little bit, get into the stinky layers of that. What we talked about before with UHPC is the bridge application, and and correct me if I'm wrong, but my understanding is the applications of using UHPC and the repairs and the videos that you have post on LinkedIn, which are very cool, by the way. I like those. I think when you say expensive, that's all you got to think about. If it was a bridge that just needed repair or replaced as a whole,
Okay.
are the two options, and you can repair it with your UHPC, or you can tear the bridge apart.
Yeah.
I think what we're forgetting about is what goes on these bridges. Lots of
Good
traffic,
point.
right? And what's
Yep.
so the cost of not having normal traffic on that bridge,
Good point.
you know, if even if you have to take a lane out and build a lane, we've all been there, right?
Yeah.
You're on a highway or freeway, and it's 3 or 4 lanes, and all of a sudden you get to the bridge and they're doing a replacement or a repair, and it goes all the way down to one lane, and all of a sudden you're sitting in traffic for 4 or 5 times longer than you typically do when you're traveling that direction. That's a cost.
I'm
Time
with you,
is
man.
a
I
time is
should
a
say value.
valuable asset.
Yep.
So
I should say value. I think as a friend of mine, I'm not defensive, right? Every time I speak about UHPC, there's always, somebody in the crowd's like, it's too expensive. So now I just put it out that it is more expensive, but it has a better value. I think value is a much better term than expensive. Again, life cycle. The stuff just lasts.
mhm.
Um, and you're not repairing and you're not creating those traffic jams you're talking about. So, and you don't have trucks burning fossil fuels to bring repair materials. So, yeah, in the big picture, it's actually more cost effective. A friend, colleague, respected professor I know, Dr. Simon Chow, did a mock up proof of concept at Dallas Airport where they were repairing a runway. Now, runways aren't just contiguous pores like highways, they're actually many domino blocks. They're big blocks that are 12, 15 inches thick. So his proposal was the traditional method is jackhammer it out, tie up that part of the airstrip, fill it up with regular concrete, wait a week, heat cure it, and then you could start using it again. His concept was make it thinner because you can make it up to 40% thinner. It's so much stronger. A thinner panel of UHPC domino. Come the day of, rip out the old one, drop in the new UHPC panel that's not as thick, connect it to the other existing panels with UHPC, and a day later you could be landing big planes on it. Now, when you did the analysis, the bottom, and it was a very ABC project, accelerated bridge construction, in this case, accelerated panel construction for an airport.
Yeah.
But the difference in cost was the traditional method with time and everything else was about 550,000 for one panel, and his research showed it's a little under 300,000. So he saved time, and he's got something that's never going to most likely have to be replaced again. So yeah, there's the value aspect more than just it's expensive. So I- I'll get over myself and stop preemptively talking about how expensive it is because your point is very valid.
Yeah. Well, you could start off and say, hey, initially when you look at it, it looks expensive, but you got to think about these other things. Saves you time. You know, especially at an airport, I imagine. If you got to shut down, you're not getting as much air traffic in there. That's big. That's big money.
Yeah, those traffic jams are much more expensive. Yeah.
Yeah. So we you explained what UHPC is. Just to remind folks. I think I don't know how many episodes you've done now. 2 or 3, 4.
I think four. This is my
Yeah,
fourth.
4. Okay, so you can go
You're
back and
becoming
listen
so
to those.
popular, you're losing track. You're so
I,
popular, you're losing track of all your podcasts.
uh, yeah, something like that. Uh,
Yeah, yeah.
yeah, so you can go back and listen to all the episodes we listened to, and I think each one has, we kind of I learned as we had our discussions, Bill, my initial thoughts on UHPC, and then today my thoughts have changed of UHPC itself. So I encourage folks to go back and listen to those other episodes. You just need to go to the website and you type in Bill Kulish, and all of his episodes will come up. What? So we're not going to talk about bridges today. What are we going to talk about, Bill?
I'd like to talk about this stuff.
Uh huh.
And for those that can't see, I'm holding up a 50 cal shell. I'm pulling up a 5.56 green tip AR armor piercing, a 30 cal armor piercing, and I wanted to talk to Seth and his audience today because what provoked some recent testing I did, we actually just got the report yesterday, is NIJ uh, depth to threat level penetration. And the reason I'm talking about it is I was like all of us, I like cruising around YouTube and looking at videos and looking at different things that's done with concrete in general. Um, and I've seen some videos where they're waving the American flag, they're behind sandbags from 100 yards, and I'll explain why that's important later. And they're shooting a 50 cal, and there's dramatic music, and it's slow motion. Um, you know, great video production. Um, but then when you go to an actual lab, and the way they do that is they're 25 feet away. They pack their own bullets on site to replicate different threat levels. Well, because it's 25 feet away, that's muzzle velocity. I mean, the bullet is as fast, it'd be like sticking the gun tip right on whatever you're shooting. And that's a whole different world than 100 yards back because the velocity decreases dramatically. So my goal was to um, counter that, as theatrical as it is, and it is cool to see. And I wanted some real science to back up. Yes, I'm guilty of having one of, maybe not a video, but some pictures of we stopped a 50 cal at this depth and everything. But I thought it was time to get into science. It's got to be replicable, and the standards are much stricter, and the projectiles are much more damaging. Um, that's what, there you go. There's your setup. So you're 25 feet away. You can see on the left, for those that are not seeing it, we have a machine that can put different barrels on it. Each barrel is a different bullet. And they shoot it. They have two devices, and I got permission to share this. You can see those two rectangles, and if you're not seeing it, they have a trip sensor laser, and then they have a exit sensor laser, and it literally clocks the speed. It's like a radar detector for projectiles. It clocks the velocity of the projectile as it goes through, and then it hits the target. And I want to note that the target is not angled, because I've seen videos where they're angling targets. Well, you can skip a rock pretty easily. You can skip a bullet on water. So everything is highly precise, measured, perpendicular, parallel. It's truly good science, as we learned. And I can expand on that a little later. But that's what I'd like to talk about a little bit today. A ballistic projectile could be a 2x4 in Hurricane Alley. It could be, so it's not just bullets, but the idea is if you can resist certain projectiles, ammunition. What Seth's showing right now is a 9 millimeter and a 44 Magnum handgun shot at extremely close range. I don't have the velocities memorized, and if you could see this picture, you would see baby little quarter-inch craters. So I mean, uh, pretty good resistance. And again, that could be a 2x4 in a hurricane. There's many, your imagination can apply all the different type of concepts that this science and these testing results will show why it could be very beneficial.
So this picture we're looking at, what's the scale? What we're looking at? That's a close up
You're
shot.
you're looking at a 1 foot by 1 foot by 2.5 inch target, and we weren't optimistic, so we brought a real thick target for handguns. All the math says when they model is that we could have done this with 1 inch, but whether it was 1 inch or 2.5 inches, you're only getting about a quarter-inch crater. So it was shot repetitively. It has to be shot NIJ standards. You have to shoot in a certain way, a certain pattern,
Uh-huh.
and this was shot um, uncharacteristically twice. So normally you need one sample per threat level. So you would have normally a star pattern on a 9 millimeter. Well, they started shooting it and they realized it was denting it. I mean, it was ridiculous. So they actually modified the test. It's still acceptable. And then they shot it with a 44 mag, which obviously has a little more power behind it. And what you see is the result of it getting hit with two of the most threatening handguns that are available.
Mm.
And it just kind of bounced off. So, yay. Um, that's
So
what
they
this
shot the
picture
same.
shows.
You're saying they shot the same spot twice.
Yeah, they shot in some cases they shot it twice, in some cases fresh. Um, because normally you only want one target because it cracks, right?
Uh
There
huh.
was no cracking whatsoever. And as the the gentleman shooting said, God, we could just sit here all day and shoot it. I think I sent you a picture where they got frustrated at not damaging it, Seth. It's yeah, that one. So here here they're like, okay, enough is enough. This is ridiculous. It wasn't cracking. They
Uh huh.
normally would only shoot 5 shots, like the number 5 on a die, one in the center, one in each corner, because they want to check the edge failure, right? And they're shooting and they're shooting and they're shooting. They hit it with a 50 cal. They hit it with multiple. They're called 5.56 armor piercing projectiles,
Uh
30
huh.
cal, and they just kept shooting. And all it would do is make little powder puffs. Worst case, it would stop at about 2 inches in. So they said, okay, we're done testing. Let's have some fun. And they wanted to shoot it until it started cracking. And then it just wasn't going to crack because of the fibers that we talked about. The fibers don't really do anything to compressive strength. They stop the propagation of microscopic cracks, which become macro, which become visual, which eventually hinge. You'll rarely get catastrophic failure with the fibers. You'll get a hinging effect, but they couldn't get it to crack, so we just called it a day.
Well, what is this with the 50 cal? That looks like a crack.
Yeah, that's a 50 cal.
Yeah.
So two things to notice. You'll notice that the surface is white and then it's like a darkish gray.
Yeah.
These samples, to be conservative, right, and not recreate the great movie effect. We were in West Virginia doing a bridge. They had leftover material. We brought forms. We made these forms on a bridge 13 days earlier. Now, it was West Virginia. It was like 32 degrees, miserable experience. Succeeded, but nonetheless, swing the truck over before you get rid of the waste. Fill up my little forms that we built. My material, when it's 100% cured, is all white. So we're literally shooting something that's a baby. This is 2 weeks old, roughly.
Mm-hmm.
And I know that because I can see the dark gray. I have some unicorn particles in there that will not crystallize for a while. So what you're seeing is a teenager when it comes to my material, and we still got the projectile resistance. We still got really good data from it at the NIJ certified lab.
Yeah, that's interesting. So you were approached to do this?
No, we have a strategic advisor who was so enticed and who has arranged and has been on the live range uh, multiple times, where we bunch of guys with guns at different distances, and he was so impressed with that. He said, "You know, that's great. We got a bunch of data from a live gun range, but all those variables we talked about, the angling and everything, let's go to an actual NIJ." And he funded the certificate. He funded the testing at this lab because he wanted to have the science, and he wanted me to have the science to actually be able to document instead of just claiming and showing pictures and videos. This is a NIJ standards are extremely strict, and this is a certified laboratory in Maryland.
Okay. What's NIJ?
I don't have the acronym memorized, but I tell you this: if you just Google it, NIJ standard, you will see what it is.
Let me see.
It's a great question, Seth. I wasn't prepared.
NIJ standards are the nationally accepted standards for body armor worn by law enforcement and corrections officers.
Yes, and it's
Huh.
beyond body armor. It's also other protection panels and such, but it all
Okay.
falls under NIJ.
National Institute of Justice. To even know that existed.
Oh, they have things that existed I wasn't even aware of. But yeah, this is how, this is a lab that, say, the military would use to test things.
Yeah.
They would send different things. And it's not just concrete, of course. In fact, this was the first time this lab had been exposed to concrete. They're normally shooting body armor, they shoot steel. The 50 cal that we passed on at 4 inches would go through a 1.5 inch steel plate. So their focus isn't what they're shooting, it's how it's shot in a controlled environment, just like an ASTM uh,
Yeah.
protocol. You must do X, Y, and Z. But unlike an ASTM protocol, where they leave gaps for people to extrapolate and interpret, this thing, everything you do, they measure humidity, they measure everything so that it's extremely repeatable and it's highly regulated. So your results are very accurate, versus the cool video in the middle of a field.
Yeah. Huh. So what's so they like the product. So what's the result?
Understand? They like the product. Um, yes, I am allowed to say that there's a scale of
Uh,
resistance, and it just you can substitute the word projectile, right? Hurricanes and stuff.
yeah.
But the resistance is at different levels. So for handguns, you normally go up to a level 4, which means it can stop X amount of energy, per caliber. We're at level 6 on the handguns, and it's not hard to understand. You look at that 1 foot by 1 foot, and you hit 44 mag and a 9 millimeter, and very quickly you can see that it certainly will stop that, right? So
Mm-hmm.
that's at a 6, and then all the rifles and everything else, with the exception of the 50 cal, and I'll explain this because I learned a lot. It was a humbling experience. With the exception of the 50 cal, we're at level 6. It doesn't go any higher. So now it's a matter of modeling it and producing thinner and thinner panels. Again, I went there not pessimistic, but I went there not wanting to have stuff go through. So the thinnest panels we brought 5 panels. The thinnest one we brought was 2.5 inches thick.
Huh.
Well, the handgun chipped like a 1/4 inch out. Of course it passed, but we want to go back now and see how thin we can really go. Now I want to explain briefly the 50 cal. The 50 cal is an unusual animal. It's very theatrical. It is not the thing that most people are worried about in war. The thing they're worried about, I'm told, thank you for your service, everybody that's educating me. I'm told it's the 5.56 green tip. So that 5.56, here's a 5.56 green tip. It's about 2 inches long, maybe a half-inch barrel diameter. Here's the 50 cal, right? You would think that this is the thing you want to protect yourself from. Well, this is rarely used. If it is used, it's used for snipers from well over 100 yards away. It could be 500 yards away. It could be 1,000 yards away.
Yeah.
So two different animals. This is what is used the most, and this is one of the most deadly. They call the green tip because it has an extremely hard tungsten tip, and tungsten, as you know, it's a pretty hard animal. Its velocity is off the charts, so it's got a smaller footprint, and because of that, with the velocity and that tungsten tip, it's badass, right? So this is the one that we're focused on. This one will do for theatrics and because YouTube people like to see this, but this is your animal. And then the 30 cal is another one. 30 cal AR this is what's used, right? These two. So this is what we were focused on. When we shot this one, which is bad, this guy was stopped on 2.5-inch thick panels. Not even halfway through, right? So now we got to go back and make it, let's say, 2 inches thick, right? But the bottom line is we got the rating on a realistic thickness. This guy took 3.5 inches, right? He's got more power behind him. So we got two different ways to look at this. But that was the goal. This was our preliminary, get our feet wet, learn how this stuff works, learn what it actually means. Now, the 50 cal, this gets interesting. Again, they're shooting from 25 feet away. This is normally used at like a minimum of 100 yards and quite often 500 yards. The problem is this is muzzle velocity. Because of this setup, there is no distance. And for every foot, the velocity slows down, right? Makes sense. You throw a baseball, and when it goes far enough, the further it goes, the slower it gets, right? So this guy trying to shoot this in a certified lab at 25 feet, to reproduce as if it was 100 yards away, they have to run all kinds of modeling. And they actually go to the rifle's manufacturer, the 50 cal rifle, and it gives you a chart of the velocity of the projectile at different distances, right? So these guys had to extrapolate and make their own bullets by putting in the amount of power that it would replicate distance. But they first shot it point blank, which is called muzzle velocity. There is no distance. The bullet doesn't slow down. It doesn't have a chance to. So when we shot the 4-inch with this, it went through. And I was like, oh, that's a bummer because we've stopped it on a live range at 2.5 inches, right? And then they explained the physics. And they said, Bill, that's not, it doesn't work that way. So then we recreated 100 yards they decreased the number of grains. And when they shot that, we stopped it. And what the guy told me was if you were 100 yards plus on a live range, the further back you went, the less it would take to stop it. So he was blown away because he's used to, again, shooting metals and really existing hard objects. So that's what we learned from that this is more for show on YouTube than it is for real world resistance.
Right.
This is what people really care about in the community.
Are they talking to you about its resistance to explosives at all?
There are tests for explosive resistance that this lab is capable of doing. This is kind of step one.
Okay. Because
they're not, but I got to be clear though, they're not talking to us about anything. They're hired to do NIJ certified testing. We're on the planet, Steelix on a planet to make a material. The logic is that testing goes to the right people with my material, and they design based on that testing. They come up with things they want to make with it, right? More
Okay.
than selling. Yeah.
I gotcha.
Okay.
Yeah. Well, I just with the way you're talking, just putting two and two together, just thinking of
Yes,
what
sir.
it could be used for. I think that the same people would be concerned about explosions.
One way and you're right, Seth. The chain of thought you just went through is exactly what I would like your audience to do. And the things that could be done: shelters,
Uh,
safe rooms, hallways in schools, doors and hallways in hospitals, police stations, banks. So that's exactly why, to start, we need this kind of
okay.
recreatable,
Yeah.
accurate data, right?
Yeah. Yeah. Well, I have all kinds of things in my head. I've been reading. I don't know if you read. I'm reading a lot of fiction lately. I'm reading Jack Carr. I don't know if you heard of him or not, but I
Yeah,
got onto.
yeah, yeah.
There's a Amazon Prime series, I guess, that's based on his books, Terminal List.
Yes, sir.
So I'm in.
Good stuff.
I don't know how many books I've read of his now. 5 or 6 now, maybe five. Five. I'm on number 5, I think. So if you read that book and then I'm talking to you about this, I was like, well, there's all kinds of things this thing can be used for.
Just
Uh,
and it can. Here's the cool part, Seth. In that case, you have you know, movie, right?
uh,
This is where the science starts to catch up with that stuff. I
yeah,
mean, look at Star Trek. Years ago. Someday they'll have these handheld things. Well, now we have cell phones. I mean, if you're really old, you look at Dick Tracy talking on a watch. We got that. So the stuff that was kind of interesting is the line is getting pretty close, right?
yeah,
That we have a material that weighs less than steel, that can stop things and anything: hurricanes, splinters, two by
yeah,
fours, projectiles, shrapnel from explosives. And we have that, and we have a way to prove that it's actually there. Now we hand that to the smarter people than me, the structural engineers and people that are military based, and we let them run with it. We gave them the cake batter. Now they can make the cake the way they want. They can
yeah,
make it bullet resistant.
yeah. Huh. That'll be interesting. Well, um, yeah, to follow along and find out what they end up making out of it as
I
you
look forward to it.
yeah as you progress through these steps. Well, cool. Was there anything else you wanted to talk about today?
I think that was my main excitement because it just happened yesterday.
Oh,
Um, so
it's new.
that's what got me pumped up. I'll
Uh,
de-animate if there's any questions you have about UHPC. I could, if you don't mind, if we have a little more time, I just want to talk about a challenge we had on a bridge, if
yeah,
that's
go.
okay.
Yeah, go ahead. We've got a few minutes.
Okay, so we're in West Virginia, and this ties into our opening discussion prior to talking about UHPC. So we're on a bridge in West Virginia, and it's 35 degrees. And the specification requested heating. So here was the challenge. And no matter how much you dig into the specification and you look at the ASTM for testing, there's a missing chunk of information, right? So the first thing we need to embrace is the mass. So the mass of the placement was huge, many cubic yards. And the ASTM says you make 3 by 6 inch cylinders. And then it kind of indicates that you field cure. Well, you got this little tiny thing that is losing more heat through heat of hydration than it can generate.
Mm.
Meanwhile, I got this bridge that's starting to cook, right? So there was a massive debate. They decided to do it both ways. The correct thing to do when it's below freezing on a bridge, of course, you heat the bridge.
Mm-hmm.
Trying to reproduce those curing conditioners for a 3 by 6 inch cylinder is just not reality. So the compromise was throw one cylinder under a blanket. Well, that's not right either, because that little thing is going to heat up faster than the big bridge, which is, cold. And the other one was put in a hotel room for a day and then ship it to the lab and break it. And somewhere in between, you would think, or you would hope, that they could predict what the in situ, what the placement actually was as far as PSI. And it was confusing to everybody because the state didn't know what they didn't know. The lab was struggling to satisfy the requirements. And when you test UHPC for a compressive, you use C39, you reference it, but it's been modified by C1856, which is really important stuff. You don't use cubes, you don't use big cylinders, you use 3x6. You got to make it a certain way, and you got to grind the ends, or you get shear fractures and low breaks. And the state doesn't want to see low breaks. Contractor doesn't want to see it. We don't want to see it. So we made it through all that, and I'm just giving an example of a code or a regulation of something that's specified that is very, very difficult to actually do, and it leaves a lot of room for extrapolation by anybody involved. If I said to you, Seth, here's the ASTM for driving to the store, and I said, you get the keys, you start the engine, and you get to the store. And as long as you satisfy those, we'll give you a rating. It took you 5 minutes. Well, there's so many steps in between that anybody could say, well, I put nitro in the gas, I put a rocket on the back of my thing. They're not regulating that. They're not overseeing that. So the procedure of driving to the store only talks about getting in the car and showing up at the store. And the stuff in between is for whatever anybody wants to interpret. They can do whatever they want. It's within the standard. So that's a very frustrating thing we went through. Now, temperature, time temperature, putting sensors in the bridge, they're working on that. But quite often it's, the predictive strength is always very conservative. They want to open up the frickin' bridge. Time is money, as we talked about. They're rechanneling a highway, and they're waiting for data to say they can take the forms off. That data is mission critical, but there's so many ways to extrapolate and interpret what the ASTM is. So my goal eventually is to actually have the standard fill in the gaps between making a cylinder and breaking a cylinder. And it helps all of us. I'm not anti-ASTM at all. I get it. But that's why I look forward to like the ACI conversations you were talking about, where we all get together and say, okay, this is great in a lab, but now we're on a bridge and it's 30 degrees and they got a traffic jam, and we're all waiting for data results that may or may not really talk about the reality of what's in the bridge, right?
Yeah. Well, maybe you're trying to utilize like the cylinders when it shouldn't be a cylinder test. Maybe it should be something else.
Well, it's a catch-22. It has to be. And the reason it has to be is it's how there's so many fibers in UHPC, how the fibers align. Their concern is on a small cube that you would not get a reproduction of what the material is, because the fibers would hit the walls and kind of it would be fake, although they've been within 5%. The next concern is the sheer power of the machine you need to break this stuff. When you're getting above 25,000, anything bigger than a 3x6 inch cylinder is going to require a floor to ceiling machine, and very few labs have that. And then the next concern is the nature of the material. When it's so strong, if the top and the bottom aren't perfectly parallel and perpendicular, you'll get a shear fracture. And these machines aren't AI. When they sense a break, they shut off. We've seen shear fractures because of improperly prepared cylinders not being perfectly parallel and perpendicular by 0.001 inches. You get a shear fracture. The machine says, whoa, you broke at 12,000. You take the same cylinder from the same batch and you do it correctly and you prepare the ends, and it breaks at 21,000. That's like a huge delta, right? But for the labs and the states that don't know what they don't know, 14,000 when it's supposed to be 18,000 minimum is a fail. and now everybody's going around saying, "Whoa, we got defective material." It's very postponing to the project. Forget
Uh,
about my pride and ego. I know my material's fine, but we got to go through all these additional steps because the original test wasn't done correctly. So that would be something I like to see evolve, right?
Welcome to being a concrete contractor. That's what we deal with
Yes,
all
sir.
the time.
Yes, sir. I know you do with this, and I think a lot of your audience is. Yep.
The silly cylinders. They can. Yeah, there's a
Yes,
problem.
sir.
It slows
Okay.
everything
Well,
down.
my dog is telling me that I think we're good, unless you
Uh,
have any other questions, sir.
no, that was it. I appreciate you coming back on there and sharing everything. It's exciting time over there in UHPC world. Sounds like. And we'll, of course, bring you back. And I'll put your information in the show notes so everybody can reach out to Bill. You go to the website. Again, if you type in Bill Kulish, all his episodes will come up along with his contact information if you want to maybe reach out and you heard something that you can help Bill with or Bill could help you with. All right, Bill, thanks for coming back on the show today. And folks, until next time, let's keep it concrete.
Thank you, sir.